Recording. Yeah, Paris, go ahead.
Homework, I think it was 2, they had all those different little bell curves, and they were saying which one was most.
This guy right here?
Yeah.
Okay, do you have your text with you? I don't have a book anymore. You have it with you, Paris? That's awesome. So we're on page 178, it looks like. 178. All right, so in number 2, if you have your book, they should take it out and have it, maybe you can share with a neighbor. You've got, in number 2, you've got 3 situations where you have 2 bell curves, 1 and 2. It says in each one, each of those represents sampling distributions, which would be like what we collected on the die rolls, what we collected with the coin spins in class last week. In each case, identify the statistic that you think would be the better estimator, or neither, and describe your choice. So this is fairly open-ended. Let's actually mute the board. This might help us with the board here. I'm gonna put this up. And I'll just sketch it one for that one, so we can chit-chat about it. So, Paris, in 2A, you've got, is it the tall bell, and then it's the tall skinny bell, and then the short wider bell? Okay, we got that one, and we've got this one. Which one is the tall skinny one, 1 or 2?
2.
That's 2. Okay, so this guy is 1. Okay. B is, what do these guys look like?
Tall, but one's centered and one's left.
Okay, good. So we got this one, and we've got this one. Which one's this?
2.
That's 2. Okay, this one's 1. And then 3, we'll put C down here, I guess. What do we have here?
1 in the center, and then this lower.
So a lower, wider center. And is that 1?
That's 2.
That's 2.
And then 1 is skewed to the left and it's tall.
Okay, so we got this.
Yeah.
That's 1. All right. Beautiful, beautiful. So let's just walk through it. Essentially, what's going to happen is one of those 2 bells is what's going to be indicative of the distribution your data comes from. So you do a sample on a study, whatever you're studying, whether it's coin spins, weights of Del Taco, half-pound bean and cheese burritos, whatever you're studying. I mean, you're studying something, and you're going to get a statistic from your sample that lives in one of these bells. The question is essentially asking you, which one would you rather your statistic come from? Which one and why? So in letter A, which one would you rather your statistic come from? I'm going to add one thing I'm not sure the book has there. I'm not sure it's clear. Let's assume that the parameter you're trying to capture is in the middle of each picture. Is that indicated in the book?
Yeah.
Okay, good. Are they calling it mu or p hat? P, excuse me, p?
It just doesn't say.
It doesn't say? Okay, well whatever, whether you're trying to estimate little p or mu, whatever it is, let's assume it's right there. Let's assume it's right here. Let's assume it's right here, and so forth and so on. Cool? Is that fair? So whatever you're trying to estimate is on the dotted line. So, given the choice, and remember, this is a little bit wishful. We're saying, given the choice, which distribution, sampling distribution, would you rather your statistic come from in choice A? What do you think? Zoe's saying,
2.
why Zoe?
Because it's a bigger sample that you're using, and so it's going to be more
That's not bad at all. I wasn't thinking sample size. So, but I think what you're getting at is the same thing I want to get at. What drew you to 2? It's
skinnier and taller.
That's what drew me to 2 as well. The fact that it's smushed in and it's higher. Now, what does the height of the curve imply in a probability distribution? I'm being a bastard here. I'm asking a 243 question. What does the height of the... Jamie, go ahead.
Less outliers, more clumping.
More clumping, and the height of the curve indicates, for example, there's the average. There's the average. If we move away from average, it starts getting less likely to land on that. So the height of the curve talks about how likely it is that you land on that particular value. So Zoe, the same reason that you and I both went to this curve is because you're more likely to get values closer to average.
So small margin of error.
Yes, your standard error and margin of error for a given multiple. So either one, basically interchangeable. So essentially, you've got more likelihood that your estimate is going to land closer to what you're actually trying to estimate. Whereas on the shorter, wider curve, you end up with more likelihood. So 95%, for example. 95% of your sample values would lie, I'm guessing, it's a terrible picture by the way, I apologize, but 95% of your sample values are going to land somewhere between here and here. Whereas 95% of your sample values in curve 1 are going to land something like here to here. So, although you still have accuracy, you lack what? Say it again, and much louder, Carrie Price. You're lacking precision in 1 versus precision, much more precision in 2. So yeah, I'm with you guys. Let's go for 2 in that one. Absolutely. So let's make it more interesting. B. B, they apparently both have the same precision. They've got the exact same precision. Essentially, if we go by sample size, like Zoe said, which I love, it looks like they drew from the same sample. But why Carrie, you went right to 2? Yeah, the problem with it is 2 actually targets what you're looking for. 1's missing it. It's very precise. It's just not accurate. Very nicely, it's just not accurate anymore. We got precision, but no accuracy. Now, the kicker is, if you can attribute, this is outside the scope of what the question is asking. Both of these would be interchangeable if you could figure out why this is skewed. For example, that might be a measurement error in whatever you're using to measure your statistics, or your data, I should say. So, for example, if I've got an arm down that has an inadvertent ½ inch extra on its length, and this distance is ½ an inch, all you gotta do is correct for that, and that becomes that curve. So you might, what I'm saying is, yes, ideally I want this one, but if you get this one and you can figure out why it is that, and you can correct it back, then you get the same thing for free. But yeah, I'm with you guys. Mary, go ahead.
Well, my question is, you never know what mu is.
Exactly, you don't know what mu is.
How do you know which one is on and which one
You don't. It's all uncertainty, isn't it? So this is why I said this is a bit wishful. Because we're saying, yes, all things being wishful thinking, I want to be on this distribution. Because this sampling distribution targets mu. You're right, it's all uncertainty. When we get that data point, we stick the margin of error on there because we have no idea where the center actually is. So the idea here is which one of these would you rather it be on? And then you can adjust perhaps for non-sampling error by looking at this one and go, oh, it was a measurement error. We can deal with that with a correction. No, you're absolutely correct. We don't know which one of these things it lives on.
So could you theoretically go with one and try and figure out a way to match them together?
Basically, yes. But back to your point, which was excellent, is we don't know which one is right. I mean, this is why the course is called probability, and not certainty or something like that. We don't know what distribution the parameter lives in. We don't know what the sampling distribution should look like. So all we do is we trust in our sample that it was done randomly enough and properly enough, and assuming that the center of our sample targeted the center of the sampling distribution. The central limit theorem is key here. It's guaranteeing that if we did the sample randomly and properly, that the center of that sample, 95% of the time, is going to be within 2 standard errors of where mu or a little p actually is, or actually lives. But that's, again, it's 95%, it's not 100%. Good point, Susie, go ahead.
Wouldn't that be bimodal?
Well, this is not 2 distributions, it's saying you are doing a sample and it either is in this one or some other one. So it's saying which one would you rather have it in. And all things being, I'd rather have it here, obviously. And assuming that we did the sampling, come on in, Michelle, you can sit next to the camera. Fair? Good-ish. Bob, go ahead.
Yeah, the only thing that makes one of them more right than the other is the fact that you're looking for the point that's in
That's it.
the line.
But back to what Mary said, you don't know where that lives. That's your parameter. This is
Right.
standing for either mu or little p. So he's in there, you don't know where. So again, wishful. All things being ideal, I want it to be number 2. I want it to be number 2. How about this one? How about this one? I want to hear your ideas on this one. I want to hear your ideas on this one. Because I'm not saying there's a right answer for any of the 3 of these. I'm saying I agree with the answers I've heard from you guys for the most part. I love C. Because C is, you see what, how about C? I heard, from like 10 people. Because it's like, what's the right answer? I'm like, there is no right answer. Tell me which one you would vote for and why. Karen?
I would go for 2.
She would go for 2. Why?
Just because it's saying that that's little p or mu, so I would want that sampling.
Does the lack of precision bother you at all?
I would have to look at my survey and figure out where I went wrong.
Oh, I like that. I like that right there. No, and when you say wrong,
Or figured incorrectly.
what if it was, let's exaggerate.
Okay.
I think I just made Karen's answer even more correct by doing that. in my personal opinion, I think I made her answer even more correct. So what I just did was I increased the precision on curve 1. Zoe, I made it tighter and higher. So I increased the precision on curve 1. But I think I just made Karen's answer more correct. Ashley, what's on your mind?
No.
Are you sure?
Yes.
I thought you were going to say something, were you?
Yes.
Okay. Okay, you don't have to. Please, Christian.
Since the results are like so wildly skewed, couldn't you throw out like the rare bit?
Oh, very good, friend. Very good. As a matter, it's funny you mentioned that. I was just thinking that would be the only thing saving that curve is the outliers. Here's my logic on this one. But actually, you know what? The hell with my logic. Let's come back to that, Christian. I want to hear your guys' ideas on this one. So we have a vote for 2. Do we have any seconds for 2? We like 2 because 2 centers on the parameter. Go ahead, Zoe.
Not only that, but 1 is so average to land right there and be skewed.
Mm-hmm. That's exactly what I was thinking.
That it's like it's gonna most likely land there. You choose 2 because it's actually so.
That's exactly what I was thinking, my friend. That's what I was getting at with Christian with your outlier talk. Let me hear a couple more ideas first before I get into that. I'm not saying that's right. That's the first thing I thought of. Go ahead, Lynn.
One thing about 1 is that you wouldn't want to like throw that out because it's telling you something really important.
Right.
There's a lot of things going on that 1 number.
There are. There's a lot of things going on that 1 number. And back to the idea of looking at the survey, if you can figure out why it shifted. I mean, and again, back to Mary's point, you don't know that it shifted. All you know is that's your distribution. As far as that distribution is telling you, that's what you're looking for, that purple line right there. So if you can look at your instrument and go like, oh my God, look, this thing has, this thermometer that I'm using is not set to be calibrated at 0, it's set to be calibrated at -2. If you can fix that, then this curve sits on top of this one, and it looks like that instead of this. Again, you don't know where mu is. All you know is this distribution is saying it's about here. And that's exactly why I would go with 2, assuming you couldn't fix that adjustment. Go ahead, Chris.
Wouldn't 2 be more likely to have 2 standard deviations as opposed to 1?
Let's come back to that in just in a second, because it ties into what Zoe and Christian have both said. Let's come back to that. Go ahead, Susie.
So if you don't know where mu is, how do you know which one is more?
No, you don't. What I'm saying, the question is, which would you prefer as a sampling distribution, assuming that your parameter is here, or here, or here?
Oh.
That's all, we don't know where mu is. We're saying the only thing you can do is look at your data and hope and work towards getting your data collected as properly as possible. And that's why this one makes me a little bit scared. Yeah, it's super precise, but it's super precise on the wrong parameter. So 95% of the time, you're going to be in here, right? You're going to be in here. And even with a margin of error, if you adjust the margin of error to even the most extreme value, you're going to be over here. So Chris, your error event rule, I actually would want to be out in this tail on that distribution because that actually gets me close to what I'm actually looking for. Now sure, you accept less precision on curve 2, but you also accept more accuracy. So you've got accuracy and less precision, lots of precision, not a whole lot of accuracy. And again, back to what Susie is reiterating what Mary said, you don't know where the parameter is. So the best you can do is look at the results from your study and go back and look at your survey instrument, look at your measurement instrument and say, did we do it correctly? Did anything contaminate our results? When I was changing the slides, counting cancer cells, did my thumb inadvertently hit any slides and contaminate them in such a way that did this? You may have done an amazing job in the actual collection of data, but in the one process you may have skewed your data. And this is all outside of the course of 244. This is once you're in your fields collecting your data, making sure the biases go away. And I got an email from a student from last term who's taking research methods right now. I mean, the project you're going to turn in on Thursday, or if you already turned it in today, is all about collecting data the most efficient way and the least biased way. That's scratching the surface. There's an entire course or more devoted to that concept. And that, in a lot of times, can determine whether it should look like this or whether it should look like this. Because if it's like this, more data is not going to help you, is it? It's actually going to make it worse. More data is going to make it worse because the curve's going to keep getting skinnier and skinnier and higher, and more of your data is going to miss by more and more, even outside of a margin of error, which is getting skinnier and skinnier. So, although there is no correct answer for 1, there are 2 good ones I've heard from you guys. Number 1, we like 2. Because on average, you get accuracy. Not as much precision, but at least you get accuracy. That's one great one. And the second one is, we like number one if we can figure out there's a measurement error that we can catch. We're never going to know if we're right or not. That's the whole problem. We're never going to know if we're right. We're never going to know if Del Taco's half-pound bean and cheese burritos are actually half a pound. But the data, assuming I collected it well, which I did as best as I could in a 10 by 20 shed full of 5 smelly guys, as best job as I could, I was getting consistent results. So unless every single result was off every single time, I have to think the data was okay, which means my conclusions are okay, which means I think I'm targeting what I'm supposed to be targeting, which was the average weight of that burrito. Yeah, Susie.
So using the burrito analogy.
Yeah, sure.
In C,
Mm-hmm.
that would look like all the burritos came in at like a third of a pound.
Exactly, which means that I was, assuming they actually are half,
Right.
it would mean that I was measuring them wrong in some way. And then like, oh crap. And this actually happened when I first started measuring it. I was putting the scale on the top of Travis's amplifier, which was covered in felt. You can't do that. You have to put those scales on a hard surface. For some reason, I don't understand why, but they don't register correctly. So I put a burrito on, it was like -2. I'm like, okay, it's not -2 anything. And then I realized, oh, it's gotta be on a hard surface. Use Ray's amp, which is a Marshall. Boom, all of a sudden it works. So that's a measurement, that's a non-sampling error. Excellent. Please, Ash.
What did your bandmates do when you were measuring burritos?
Drink
they
and
know?
smoke.
They just know? They're like, okay.
They just drank and smoked a lot. Sorry guys, it's true, you know. Yeah, they did a lot of drinking, a lot of smoking. And writing punk songs, that too. You want, Brooke, let's get you a chair. Yes. So yes, it was just Rule, the insane math guy, measuring burritos because that's what he does. Yes. Cool, does that make sense? Great question, Paris. Great question, and it deals with so much of the uncertainty that we deal with, but then also ways to mitigate some of it. So Mary, Susie, we never know where the center is. We never know. What we can do is we can mitigate non-statistical errors that make it more likely for us to target the center we're looking for. And it's all about the data. Everything we learn in this class is really a sequence of button pushes on technology at the end of the day. It's a way of processing data and getting a confidence interval. Essentially, that's what we're doing. But that all depends on how good the data that you're putting into that computation, how good that data are, how good that data is. How good that data is. Yeah, we'll say is, or it's plural and singular. How good the numbers you put in are. We'll say it that way. So if you got crap, you ever heard the phrase garbage in, garbage out? It's an old 80s phrase, but I like the 80s. So yeah, garbage in, garbage out. You can put any numbers you want into one prop Z in, or T interval, and you will get results out. And they were going to suck if what you put in sucked. So you saw that in your project, and you'll continue to see that as you read more and more Facebook surveys. Cool? Anything else give you agita in there? Some of the wording, I apologize for some of the symbols used in your book. It's the only book I've ever seen that doesn't use p hat for a proportion. That's why I made you guys get comfortable with p hat in class, because everybody else in the world uses that. They use p, whatever hell symbol they use. Yeah, so just p hat's what the world uses. For some reason, Stack 2 decides to be all magazine-y and different pictures. So, yeah? Technology working okay? Is everybody, I want to revisit real quick the program that I gave you guys. We only did like 1 or 2 tops examples using that program, and I want to make sure you guys are happy. Well, happy. Use the word happy carefully. Are giddy up. Are content with it and can run it properly. Let's make sure we can see this okay. Ish. Is this okay if I put this right here? I'll move it out of the way for you guys once we get done. So one prop Z in, piece of cake. There's the T interval we did last time in class. Del Taco half-pound bean and cheese burrito. We'll do more of these today. Got a little experiment put together for us to collect some more data. Hopefully some good data. We'll see how it goes. So you're getting ready to run a survey. Oh, dude, please. No apologies. No apologies. Crappy weather. So you're getting ready to run a survey on a percentage. You're going to estimate the percentage of something, whatever that something is. And you need to know how many people you need to survey. Or, actually, I should phrase that better. Actually, we'll come back to my better phrasing once we calculate the actual sample size. This is one of the 2 that I gave you that you don't go to stat to get to, you go to program, PRGM. PRGM. And I got a lot of crap in here. You guys probably have 5 things. Go find the one that says SSZE Calc, sample size calc. All right, grab that guy. First thing they ask you for is confidence. we're going to use 95 on every assessment in this class. So I know once in a while your book says use 92.3% confidence, just to see if you're paying attention, I guess. Just use 95. 90. Yes, yes.
What that's called for me.
No,
Okay.
because I have to give it to you, and it lives on my computer. Can you come by office hours tomorrow, Linz? Is that possible?
No. We'll make it work.
Can you hook that into your computer at home?
Yeah.
Then I'll email it to you. Just
Okay.
send me an email to remind me. Yeah, a former student actually wrote it for me because I didn't know how to code on the 89.
Oh.
So I will send you the program from Brian, and I will send him an email thanking him again. 95, doesn't matter if it's decimal or a whole number. It accepts either one. I rewrote the program to do that. The margin of error, though, I do want as a decimal. I ran into some problems with very small margins of error. When they were not decimals, it was getting a little bit upset. I want to talk about what you're putting in right now. Because some of you are going to say, wait a minute, rule? Damn it. How can we have a margin of error until we run the study? Because doesn't the margin of error come as a result of the study?
No.
It's a result of x and n. You do x divided by n to get p hat. And p hat and q hat over n square root is the standard error. What this is asking you for is, what is the maximum margin of error you will accept in your study? And basically, 3% is a fairly standard. I think on your quiz I had you use 2.5.
Yeah.
So let's just do your quiz problem. What the hell? 0.025, in direct defiance of my syllabus saying we'll never talk about quizzes in class. 2.5%, make sure you put the 0 in there, obviously. Otherwise it's 25% margin of error, which is not that useful. I'm 95% confident between 0 and 100% of people like this thing. So there we go. There we go. There you go. 1537. Now, those of you, if you've tried to crank this by hand, some of you, if you use, so when you put this in right here, this 95, the TI, if you look at the code, which I don't recommend that you do, because it's easy to erase things in there, the code is actually using that to calculate an area on the curve. And it's calculating 5% area, 2.5 and 2.5 in the two tails. The actual z-score that does that, I've forgotten now. It's, let me do it real quick here. It's in norm 0.025. Yeah, we call it 2, or -2, depending on which side you're on, but it's actually closer to that to 10 decimals. So if you use 2 instead of that number, you're going to get a slightly different answer by like 50 or 60 people. That's exactly, and that's what you have to use to multiply your standard error to turn your standard error into a margin of error. So that's what you'd actually have to use to get exact 95% confidence. By using 2, hang on, I'm using the shortcuts here just because, let's go from -2 to 2. By using 2, you're actually doing 95.45% confidence. So we rounded off to 2 for discussion in class, 68, 95, 99.7. But that's why if you try to crank it by hand, you might get slightly different answers than with the machine. But I built the machine for you so you wouldn't have to do it by hand. So by all means, use it in good health.
And we thank you for it.
Oh, no, you're welcome. You don't have to thank me. It just makes your lives easier in the learning process. You're welcome. One thing, though. This is the number of people you have to get responses from in a simple random sample. Just a heads up for the... Ian, answer that question.
Oh, no,
Are you sure?
yeah.
Okay, I'm sorry. If I ruined it, I'm sorry. I saw a question for me. Maybe I'll stop talking now. Maybe it'll come back. That's the number of responses you have to get. Which means if you go ask 1,537 people, you've got to get responses back from all of them in order to satisfy 95% confidence, no more than 3% margin of error. Chances are you're not going to, because there's a response rate that usually happens, and you'll study this in survey classes. Very often, you get like 10% responses back, which means if you need that, you've got to go ask 10 times as many to get that many back. So it's called sample size calc, on the ideal wishful thinking that if you ask that many, you'll get that many, but you actually have to get that many results at the end of the day. Ian, go ahead now.
I answered it.
Oh, you did? You're the man. Awesome, awesome, awesome. Go ahead, Karen. Do you have a question?
Sorry.
I'm seeing motion. Like an amphibian. I just keep seeing motion. I figured it's a question. Bob's taking a drink, so I'll have to ask him. Okay, we're good.
I do have a question.
Go ahead, Jamie.
I mean, this might actually seems kind of silly, but you said you need 1,537 responses back, and if you sent out 10,000, how do you sort through? Do you just collect the first 1,537?
What I'm saying is if you ask 10,000, you won't get all 10,000 back. Or if they start the study, they won't finish the study.
But what I'm trying to is,
Mhm.
when you get them back,
Yes.
to keep it so that it's,
Oh God, no. If you get more than that,
That's better.
then you accept a smaller margin of error. You get, oh crap, you get this instead of this. That's a minimum sample size to achieve no more than 3% margin of error or 95% confidence, and 95% confidence. So if you get more, hell yeah, but you've got to get at least that to satisfy those. That's a great question. Yeah, accept it, as long as it's good data, remember, as long as it's good data. Because if it's more crap data, it ends up looking like this. You got tall, skinny precision on an inaccurate center, which is great, if you can figure out why it's inaccurate, which we never know, as Mary and Susie pointed out before. So that's, I wanted to make sure that you guys could run that program again too, because that one right there, in case, you can do them by hand. It's a nice manual calculation. I think it's just like z squared over e squared times 0.25. But this does it for you, and it takes care of all the messy calculations of what the z-score is. So, use it in good health. Or use it in the snow, whatever. Cool? Ish? Cool. Yeah. So that's